So I am Arthur, and this is Dave, and we are teaching. Yeah, first of all, some, I guess, administrative stuff. So let's see if this is working now. Well, it should work. It is not working. It should work. That's weird. Yeah, let's see if that works now. It still doesn't work. That's annoying. Okay. Anyway, yeah. So yeah, I will be doing the part on kernel methods, and Dave will be talking about reinforcement learning. So it is, I guess, a sort of high-level course on machine learning. So I guess there is like some reasonably tough background. But I think, yeah, generally speaking, it's reasonably self-contained, and so yeah. Probably of the two parts, mine is the more mathematical one, or that's what the students mentioned in the assessment. But as it happens, well, the course can be sort of taken in two individual parts on their own, more or less. So there's reinforcement learning, there's kernel methods. In the exam, unless you're from Gatsby, you can actually avoid taking one of the two parts completely. So the assignment, there are two assignments, and you get sort of the grade of the highest grade of the two. And in the exam, there are going to be 6 questions. You can choose 3 from entirely one part of the course. So that's actually by design, in that if you're interested in reinforcement learning on its own or kernel methods on their own, you can do one or the other. But yeah, nonetheless, we sort of encourage you to sit in on both parts of the course, because like I think the tools from each of them are really useful. So I hope that, yeah, but you know, if you choose not to sort of study for one or the other parts, you won't be penalized for that, unless you're from Gatsby, in which case you do need to pass both of it, but that's a separate issue. Yeah, so we will also be using just 1.5 hours of each 2-hour slot. So the Tuesday session, I think, is scheduled to start at 9 o'clock. We won't be that cruel. It'll start at 9:30.
Thursday.
On Thursday, yes. And this session is going to go until 3:30 and not until 4. So there is one special case, because we couldn't get this beautiful room on one of the days. And so on the 19th of February, we will be in Roberts 110, and it'll be a single 3-hour block. There won't be anything on Thursday. So that's something. So also, just for emails, we have a sheet. So if you can, everyone just write an email down on it.
Just write your name.
Then, like for stuff like anything that we think is interesting, we'll send out to that list. Okay, so I'm going to just quickly discuss the outline of the kernel bit, and Dave will talk about the reinforcement bit. So the first, yeah.
When can we get the lecture notes and slides?
Yeah, sorry, lecture notes are going to be online. So they're actually already all up for my part, and I think for Dave's, because we taught it last year. We will, so I'm going to update my slides in answers to questions and stuff, like I did that last year as well, and that seemed to work pretty well. So next to the slides is going to be a date, and that's the date when I last updated it. So if you see that the date is like obviously later than we've got, then you can download the latest version. Yeah?
Just one quick point about the slides. I printed them off, but they sort of printed off as it kind of adds little bits to show up on each slide. So like there's 30 slides, but there's like 140. Is it any possible to have it so like the final version of each slide is?
I don't know how to do that. But yes. Bear in mind, can you do that?
Yes, you can.
Okay, then Dave will show me how to do that. Yeah. But in any case, the slides, I think, are accompanied by lecture notes, which are the sort of like textbook version of what's on the slides and have more detail anyway, so you might want to go with that. But the slides are also kind of nice. So, yeah. Okay. Yeah, so basically, it's going to be, I guess, like a lot of you, I mean, hands up who's done some sort of kernel stuff before in previous courses. Like, I guess a lot of people, right? Yeah. So this will be perhaps a more mathematical sort of approach to this, and won't necessarily, I mean, it will cover at least some of the stuff that you might have covered already, like large mathematical classifiers and ridge regression and so on. But it's also going to cover things that you probably haven't seen elsewhere, like how to do two-sample testing, so testing whether two samples are from the same distribution, things like independent component analysis, feature selection, clustering, like a whole bunch of stuff which is perhaps in the more advanced and more cutting-edge, I guess, parts of the kernel research area. So in the sort of spirit of continuing to have parts of the course that don't need to be assessed, the final part of the course is going to be like a theory section. It's going to be just, I guess, the last 2 or 3 lectures, where we're going to basically recap the initial parts of the lecture, but in a technically rigorous way so that mathematicians are not, I guess, annoyed. And so that part isn't going to be assessed. But at least one mathematician last year was sort of saying that should have been here, but then everyone else disagreed. But nonetheless, it will be, and the notes are already online, so people who want rigor can already see the rigorous version of it. So I think maybe, Dave, do you want to talk about the RL?
Okay, sure. Quick switch over. So hi everyone, I'm David Silver, teaching the other half of the class. Let's see if we can make this work.
The quote is a bit short.
Oops.
Yeah.
Maybe.
Swap the electrons as well.
Do you mind if I just
Sure.
pop this over here? There we are. Okay, so you can think of this course, Advanced Topics, as essentially it's almost like 2 half courses. And as Arthur was saying, it's possible to actually take them independently. If some of you, are really much more interested in one half than the other, it is possible to go through the whole course focusing on one half. We'd really encourage you to go to both halves because there's a lot of interesting material on both sides. But we just wanted to emphasize the way it's taught is such that it is possible to focus on one side or the other. And these are really sort of 2 separate self-contained courses. Okay, so just briefly, I'm not going to go through all this today. This is actually the first lecture, which will come up on Thursday, so please come along. Basically, all I'm going to try and do now is to persuade you that it's worth waking up and going to a 9:30 a.m. lecture on Thursday. So I'm just going to give you a bit of background. So very briefly, I mean, Arthur's already mentioned this, but sorry, this is, okay. So the assessment, so it's actually Thursdays, sorry, this is last year. So this is actually going to be 9:30 to 11 in the morning. But this website is exactly, someone asked the website, so I thought I'd flash up this slide. This is the website where all the class notes for my side of the course will be placed. There are also links to Arthur's and vice versa, so you can find it from there. And if you need to contact me for any questions, this is my email address here. Okay, so Arthur mentions the assessment. The assessment itself will be 50% coursework, 50% exam. And the examination, and the idea of the coursework is actually that we'd encourage you again to do both pieces of coursework, but you'll actually be marked by the max of your coursework scores. So there's a real advantage to sitting both parts of the course, and actually whichever one of those you do better in will be your final score on the coursework part of the assessment. And similarly to the examination, there'll be 3 questions from each side, and as Arthur mentioned, you get to pick any 3. And so the advantage of sitting both sides is you get to pick the ones that you feel most comfortable with, so you get more choice there. Okay. I'll talk about this on Thursday briefly. Okay, so I just wanted to talk very briefly about what is reinforcement learning. So reinforcement learning is essentially this thing which sits between many different fields, and essentially you can think of it as the science of decision making. And really, there's views of this from computer science, which is what we would do in machine learning, and that's the sort of aspect that we'll be focusing on most of all in this course. But also neuroscientists care about reinforcement learning because of the reward system. Psychologists care about reinforcement learning. This is what's called classical conditioning, like Pavlovian conditioning and so forth. Economists care about it. They have notions of bounded rationality and so forth. Mathematicians care about it. They have a whole field called operations research, which essentially covers the same material that we'll be covering in reinforcement learning, but from a different perspective again. And engineers, they care about reinforcement learning. They want to build systems that are able to make good decisions in practice. And so they have a whole field called optimal control. And really what we're going to be doing is learning about the core ideas which are central to all of these different fields of decision making. And in particular, we're going to take a machine learning viewpoint on this, so there's different languages you can use to describe the same ideas. This is a machine learning course, so we've taken the machine learning viewpoint. So within machine learning, you can break down machine learning into areas that you're probably more familiar with, and which you've already seen classes on, supervised learning and unsupervised learning. And what we'll be focusing on in this part of the course is reinforcement learning, which is a distinct paradigm. It's one of the three main paradigms for machine learning. So in supervised learning, there's some teacher that gives you the signal that you need to learn from and tells you what's right and what's wrong, tells the learning system what's the right answer, and it learns to do better. In unsupervised learning, there's no teacher at all, and the system just needs to figure out something, say, about the distribution of data that it's seen. In reinforcement learning, there's a delayed feedback signal, so it gets some kind of reward signal saying, is it doing well or is it doing badly? And from that delayed feedback, it needs to figure out for itself what the best course of action is. So no one tells it what's right and what's wrong. It's just like if you're teaching a dog how to behave, you give it a cookie if it does the right thing, and you hope that it does more of the right things in future. So it's very distinct from either of these two paradigms. Okay, so what's interesting about reinforcement learning compared to the rest of machine learning, there's no supervisor, just a reward signal, and you get this delayed feedback signal. So it doesn't happen straight away. There's no one saying right or wrong immediately. You have to take a whole sequence of actions over real time, and at the end of that, after this whole sequence, you then have to just, get some reward signal saying good or bad, or some number in between, just a real number saying the effect of that, the effectiveness. And what would examples of this be? So I think it really helps to get some sort of real-world examples to make this all concrete. And these are real-world examples which are really very much based on the ideas that we'll learn in this course. So if you sit through the whole course, you'll have a pretty good idea of how each of these different ideas was actually done. So these are examples of things which have actually been done using reinforcement learning. So flying stunt maneuvers in a helicopter, defeating the world champion at a game of backgammon, managing an investment portfolio, controlling a power station, or making a humanoid robot walk. These are all examples of sequential decision making where some kind of agent had to take a sequence of actions so as to optimize some long-term reward signal. Where in a helicopter, the reward signal might be something like following the flight path of a human example, or it might be something like avoiding crashing is the obvious one. If you crash, that's bad. You don't want to crash. Big minus reward for crashing. Or winning at backgammon, you get a win or loss at the end of the game, and you just want to learn how to take actions such that at the end of the game of backgammon, you win as many games as possible. Control managing a portfolio, you want to take the sequence of trading decisions such that at the end of your trading decisions, you get the maximum profit. Controlling the power station, you want to turn all the different controls on the power station so that you maximize the throughput of power production in that power station. Or making a robot walk, the idea there might be to stay upright and make progress along the ground. Okay, so I just wanted to have, just to make this even more concrete, one video, and then I think I'll pass back over to Arthur after that. So this is a helicopter. It's not full size, but it is fairly substantial. That uses reinforcement learning techniques to execute a series of very, very challenging maneuvers that human pilots actually found very challenging to do. If you look at it, some of them are crazy, like it's actually flying onto the back of the upside down and drifting over, it's doing loops, it's doing all kinds of crazy maneuvers. In order to do this, it has to work out a whole complicated series of both planning and reinforcement learning problems. And if you come along on Thursday, I'll explain what those different things mean, what the components are of systems such as this that are able to perform complicated sequential decision-making tasks. This one's called the Hurricane here. And finally, there's knife edge, stationary rolls. Anyway, just a bit of fun there. So, okay. So I'll just conclude. So this is Thursday. So I'm not going to go through the course outline in detail, except to say there's going to be two major parts to it. Beginning, we'll talk about the elementary methods of reinforcement learning, going through an introduction, what Markov decision processes are. This is like the problem setup, formalizing the problem that we need to solve for such that any of these problems we discussed, the helicopter, the power station, and so forth, they can all fit into this framework. And then we'll talk about methods to solve Markov decision processes, planning methods. We'll talk about how to achieve good results in Markov decision processes when you don't know the model of the system you're interacting with, which is these methods here. And then the second part, we'll talk about more sophisticated approaches, really bring us up to state-of-the-art methods for dealing with these approaches. And finally, we'll conclude with a case study, which is from my own experience working with reinforcement learning in computer games and board games. So that's roughly an outline of the course. So 10 lectures, Thursday morning, 9:30 a.m., but hopefully worth waking up for. Okay, back to Arthur. I should say as well, I'm probably going to drop out at this point, so if there's any questions specifically about what's going to be happening on Thursday, then now's your chance to ask. Otherwise, just please come along and there'll be more time to bother you. Okay.
Okay, so I'll start with, I guess. So by the way, like, the first lecture, I guess, is going to be quite technical, and so you are very strongly encouraged to like interrupt me whenever stuff is not clear, because it's also stuff that you probably need quite seriously for the remaining things. So I'm going to go slowly, but I will sort of warn you that this is perhaps one of the most mathematical parts of the course that I'm starting with, because unfortunately we need it. So I'm sort of the bad cop and David's the good cop. So what are kernel methods for? So I think there were two viewpoints that people have used when describing like what are kernel methods for and how they work. So one is in terms of sort of features of the variables that make learning easier, and one is in terms of sort of smoothness of predictive functions, so like a well-behaved predictive function. So what do I mean by these two things? So here is the example of the first viewpoint. So let's say that I have blue points and I want to separate them from red points that live in a 2D plane, and I need to sort of make some sort of linear classifier to separate these guys. So obviously, like if I put a straight line anyway here, I'm going to make a lot of mistakes. So I can separate at least some of the blobs from the others. Like I can put a decision boundary here to separate this red guy from these two blue guys, but then I'm making an error on this red set of points there. But what I can do now is to find nonlinear features of these variables that allows me to use like a planar or linear separator between the two classes. So let's just say that I add just a single extra dimension. So I've got my two initial dimensions here, my red blobs and my blue blobs. And then I'm adding a single extra feature, which is the product of the two coordinates, so the product of x1 and x2, okay? So the points in the positive and negative quadrant are going to be pushed upwards. You can see that here. And the points in these quadrants here are going to be pushed downwards. And then I can just put a flat plane through the origin, and that's separating the red from the blue with 0 error, okay? So this just gives you this idea that you have a difficult problem, you can't find a simple linear classifier. But if I use now some nonlinear features of my variables, then I can start to use a simple linear classifier to separate them. And so this is sort of one interpretation of kernel methods, is like find a good space of features to make problems easy. There's another reason that one might want to try and find features. So imagine you've got like two piles of documents here, the red and the blue documents. And let's say that for each of these documents, I'm getting a histogram of the words in the document, okay? So this histogram here has like a low probability of seeing the word cat, but then a high probability of seeing like dog and kennel, and then like furry is somewhere in between. And then these documents here also each have histograms, okay? And here kennel and dog are really low probability, cat is really high, and furry is again like present. So you can imagine that like these are all documents about dogs, and these are all about cats. But here, like if you're just given a piece of paper with words on it, like what are the features of this that allows you to distinguish these two sets of documents? Okay, because these are just objects. Whereas if I now say, well, okay, here is an interesting feature for my documents. It's this histogram of the words in it. As soon as I've got these, I can start running a learning algorithm on these features, because these are now numbers I can plug into like a support vector machine and so on. So this idea of sort of taking objects of some kind, like documents or graphs or angles of a robot arm, finding some interesting numbers and then using these numbers in a learning algorithm. Like this is I guess, what follows from this idea of looking for useful features which allow you to make learning easy. Okay, so this is just one view of what kernel methods are for and how they work. Here is another view. This is in terms of the smoothness of the function being learned. Okay, so let's say that I have a set of points and I want to put a line through them. Okay, and I'm going to give you 3 candidate lines here. And so you can say, well, this one seems too smooth, this one seems too wiggly, and this one seems more or less just right. But the question is, first of all, how do you formulate a problem which is going to actually learn this line with a low error? And second, how do you control how wiggly the line is in some sort of meaningful and interpretable way? So you want to basically have some sort of knob that you can turn so that you can adjust this until you get something that seems reasonable. Maybe it has like a small cross-validation error, or there's some other criterion that tells you that you've got the right answer. Okay, so I've talked about this. Like this line here is actually obtained with kernel ridge regression, so it's the output of a kernel method. Now, from the 3 slides that I've shown you, it's not particularly clear why this is even in the same course, because the first 2 are talking about nonlinear features, this is talking about smoothing, and it seems completely irrelevant to each other. But I think quite soon I'm going to hopefully show that these amount to the same things when you're using kernel methods. So kernel methods is a way of sort of doing both of them, and they're both in some sense an equivalent way of looking at a problem. Okay. So just the mathematical foundations. So the tool we're going to be using in the kernel part is this reproducing kernel Hilbert space. So I'm going to now go through and define like these terms. Okay. So I'm going to start with the easiest one, which is Hilbert spaces, easiest in quotes, and then kernel, and then finally reproducing. But I'm actually going to skip the difficult bits and just talk about like the ideas. And for the purposes of the exam, the ideas are what matters. Okay. So first of all, Hilbert space. So I think a lot of you have encountered dot products in the past, right? So basically, first of all, I'm just going to introduce a vector space. That's a space with a dot product on it. Okay. So you've got just, you know, an object that takes 2 things and takes their inner product, like A transpose B if A and B are vectors, okay? So a dot product has a couple of properties. First, it's linear, so if you've got basically the sum of 2 vectors with some scalar, and you take the dot product with the third, it's just a scaled sum of the dot products, okay? That's one property. Another property is that it doesn't matter what order you put your objects in. You can flip it around. And the other is that the dot product of something with itself has to be non-negative, and it can only be 0 when this object has 0 length. So if you've got A transpose A, where A is a vector, then this is going to always be positive. It's just the norm squared, right? And a norm has to be positive. And then A transpose A, like the norm is going to be 0 only when A has 0 length. So it has to be the 0 vector. Okay? So this, I hope, is revision for everybody. So I hope its space is just one of these with an additional technical condition that will come in the last 3 lectures. And the technical condition is that if you have a sequence of these objects and the sequence converges, then it has to converge to something in the space. So you can't somehow like take a limit of things that get further and further away and sort of vanish out of this space. So this condition here, if you care about it, you can read about in the final lectures. These are the conditions that matter for the purposes of what we will talk about here. Okay. So now that's Hilbert space. So next is kernel. So what is kernel? Kernel is just a dot product between features, okay? So here you have basically a space of objects, which is X. Okay, so these might be a set of documents, it might be a set of like proteins, it might be any objects at all. It doesn't have to have any sort of structure on it. And then this phi is the crucial thing. So that is going to take our objects and find useful features. So it will take like my piece of paper, my document, and it's going to give me the histograms of the words. Or maybe it's going to give me like, you know, n-grams or some other useful feature of the text in the document. Or if I've got an image, it's going to give me, maybe like where the edges are, what the colors are, textures, and so on. Okay. So this VE maps X into a Hilbert space, so a space where you've got a dot product, and the kernel is just this dot product between the features. Okay. So dot product between the histograms, say, or whatever. Okay. So is that clear? Yep. Now, one interesting point is that if you've got a dot product, your features might not be uniquely defined. So imagine that the feature of X is just X. X is just a number, okay? So the dot product between X and another X, like X dash, is just the product of these two numbers. But here's another feature vector which gives you exactly the same answer. So if I take the inner product of this feature with another feature, I'm going to get exactly X times X prime as my dot product. So you can see just from this very simple example that just because I've got a dot product doesn't uniquely define my features. There may be infinitely many features with the same dot product. Okay, but ultimately it doesn't matter because they have the same dot product, so it shouldn't be troublesome. Okay. So I've sort of talked about kernels, but most of the interesting kernels that people use are reasonably, I guess, sophisticated and take into account like a lot of features of the variables that they're looking at. So one way that people use to construct these sophisticated kernels is by taking simple kernels and then like joining them together in some way. And so most of the kernels that people use in practice are actually built up from these simpler kernels. So these rules will allow you to sort of do this. So the simplest rule is that if you have two kernels and you add them together, or if you have one kernel and you multiply it by a scalar, then this is still a kernel. And why is this? Well, you can go back and you can check all of the definitions of an inner product, and all of them hold. So that's what you need to do. But if you take one kernel and you subtract another kernel, that's not a kernel necessarily anymore. So does anyone want to guess why that might be? So to give a clue, I will go back to definitions. So one of these is going to break. So can anyone guess what it might be that breaks if you take the difference in kernels?
One kernel?
Yep, exactly. So maybe this is not going to be negative. One kernel small, the other's big. Small minus big, you get a negative number, and this breaks. Yeah. So another trick that you can use is this mapping trick. So this is actually kind of a trivial trick. So you start with some space of objects, then you map these objects to another set of objects, and then you take the kernel on the new set. So here's a simple case. So you've got a scalar variable x, and then your mapping a is just the square of that number, okay? So x squared. And then you're saying, well, my kernel is between the mapped x, so not the x in itself, but the mapped x and the other mapped x. And this is fine because you're sort of taking objects, you're corresponding them to other objects, and then you're taking the kernel on the new set. But the inner product on the features of the new set is still a valid inner product, so this is a valid kernel. So this is another trick we're going to be using quite often. Okay. So here's a trickier one. Products of kernels are also kernels. Okay. So let's say that you have a kernel on one set of objects, another kernel on another set of objects. Then this is a kernel on the space of like pairs of the objects. So what do I mean by that? So let's say that I have a kernel on images. Okay. So similarity measure in some sense between a pair of images, and I've got a kernel on captions of the images. Okay. So now maybe I want a kernel on a pair of one image and one caption, and the other image and the other caption. Okay, so a similarity level between an image caption pair. And what I'm claiming is that if I take the product of the similarities on the images and the similarities on the captions, then this will be a sensible measure of similarity for image caption pairs. Because if both of the images are similar and the captions are similar, it's going to be big. If one or the other is small, it's going to be small, the product. And then if both of them are small, it's going to be really small. So like at least intuitively, this kernel is a reasonable kernel. But what I want to know is that mathematically, is it a reasonable kernel? Okay? So I'm going to prove this just, I guess, informally. So I'm going to say that my first kernel, this is my kernel, my images. So this U is a feature of one image, and this V is a feature of the second image. So then I just take the inner product between these feature vectors. That's my kernel. This is the inner product between the features of my captions. I'm going to take the product of these two, and I'm going to ask, is this a valid kernel? Okay. So is this kernel? So I hope people can, this whiteboard is kind of to one side, but I think it's clear. So I want to say is K equals K1, K2, valid. Okay, so let's see what it is. K1, K2 is equal to, so U transpose V, so that's K1. Is that pen clear to everyone? Yeah. And P transpose Q. Okay. Now these are both scalars, so I can now write is equal to U transpose V, and I'm going to write trace of P transpose Q. Okay, so the trace of a scalar is just a scalar, that's fine. Okay, now I'm going to use the property of the trace, U transpose V, trace. Now, when you're doing the trace, it doesn't matter what order you take these in, right? So now I can do P, Q, transpose. Okay? So now I can take this scalar inside here is equal to trace, and then here we've got P, U transpose, V, Q transpose. Okay, so I've taken this scalar and I've just put it in here. Okay. Now this is equal to trace. Now here I'm going to define P, U transpose as A transpose and V, Q transpose as B. Okay. Trace A transpose B. So what is PU transpose? This is the outer product of the features of the images, which are U, and the features of the captions, which is P, so for one image caption pair, and the features of the second image and the feature of the second caption. Okay. Now this trace of a product, A transpose B, is a valid inner product between this object and this object. So this is just a standard inner product between matrices. Okay. So what I've now done is I've defined a feature of an image caption pair whose inner product is defined by the product of the kernel. So I've shown that this kernel is a valid inner product on features of image caption pairs. Okay, so is that clear, or do people have questions about this so far? Yeah. So this is all in the notes. But yeah. So the proof is here, so you don't need to transcribe. Yeah. Okay, so I've shown that the product of kernels are kernels. So you might sort of think, well, you know, this trick works very nicely when I've got vectors and I can do linear algebra. What happens when you have some much more complicated set of features? Exactly the same proof works. It just has messier notation, but like the idea is exactly the same. And the idea is the important. Okay, so we've shown sums of kernels are kernels. Scalars multiplied by kernels remain kernels as long as the scalars are negative, otherwise you break the third condition. And products of kernels are kernels. So now we can use that to build even fancier kernels. Okay, so here is a kernel which is a polynomial of the inner product between x and x dash. Okay. So how would I prove that? Well, I would just expand out the polynomial, and I have kernels to some power multiplied by some scalar, okay? And so basically, I know that a kernel times itself, that's a kernel times a kernel, that's still a kernel. Sums of kernels are kernels, kernels times scalars are kernels, so everything works out. And this thing here is a kernel. So you can like write it all down and make sure that it works, but that's how you would do it. Okay. So this is all fine because this is a finite number here. But now, in fact, in many interesting cases, kernels are inner products between infinitely long features, actually. So now we're going to look at what happens when the number of features that are used in the kernel goes to infinity. Okay. So here's a very simple case. I'm going to define, first of all, the space of LP summable sequences, or okay, LP of P summable sequences. Okay. So this is basically an infinite sequence of numbers raised to some power should be less than infinity. Okay. So that's the set of P summable sequences. So there's sort of sequences that are decaying fast enough that when you take this sum, it doesn't blow up. It gets less than infinity. Okay. So the set of sequences that we care about for the purposes of kernels is when this P is equal to 2. Okay. So if, let's say that Fi for infinitely many I is a vector of nonlinear features of some x. Okay, so this is my vector of features of books or images or whatever. Now it's infinitely long. But the sum of the squared features for each x is less than infinity. Okay, so these features are in some sense decaying fast enough that for every image or for every whatever I feed into this, the sum of the squared features is bounded. Okay, then this here is a valid kernel. So basically, my first question would be like, what do we need to check to make sure that this is allowed? So conditions 1 through 3 should hold, because it's just an inner product, it just has more terms. But when I have infinitely many numbers, does anyone want to guess what can go wrong?
Well, it can diverge.
Yeah, exactly. So this thing might blow up, so we better check that it doesn't, because otherwise you're just going to get infinity, which is not a very interesting level of similarity between two things. Okay, so the trick is that because we know that the sum of the squared features is bounded, we can show that the kernel is never going to blow up. The way that we do this is using Holder's inequality. So here is the sum of the absolute products of each of these features, okay? And I can show that this is upper bounded by the product of the sum of squared features, okay? And we've said that these sum of squared features are bounded. So because we know that these are bounded, we can show that this kernel is bounded. So this is how we make sure that we don't run into this problem that we're using infinitely many features, so our kernel is just infinite and very dull. Okay. So this is one set of infinite features that one might use. Let's look at another one, which is actually probably the most common one that everyone uses in the literature, which is kernels that can be expressed as Taylor series. Okay. So just a quick reminder, what's a Taylor series? So basically, a function has a Taylor series expansion when it can be written like this. So this is a scaled sum of the argument raised to some power, okay? And we require that the absolute value of this scalar here be bounded by r, where r is like the radius of convergence. So if it gets too big, then maybe this thing doesn't converge. So we want to make sure it doesn't get too big, okay? And now I'm claiming that if my x space is Rd, and the norm is less than square root of r, so I'm within the well-behaved radius in my space, then this object here is a valid kernel. So I'm taking basically my Taylor series, and I'm using as the argument the inner product, just the standard inner product between 2 points in my original space. Okay? So this object here is a valid kernel. An example of it is the exponential of the inner product. The exponential has a Taylor series expansion, so if you write it out, you can see that this object here is a valid kernel as long as this is true. Okay? So how do I prove that this is a valid kernel? So the proof is not all that different from the one that I did already. Okay? So what I have, so here is my kernel, which is the sum of the inner products in d dimensions raised to some power n. Okay. Now I expand out this d sum, like d to the power n, and I get some non-negative numbers here, multiplied by the product over the d dimension of the the product of the ith coordinate raised to some power j. Okay. So I'm just expanding this out. And so here what we have is we have a sum of kernels, which are just inner products between the ith feature raised to some power. So now here, all that we're doing is using the same, sums of kernels, products of kernels, kernels multiplied by non-negative scalars of kernels. All of these things we just use again. And we get that this thing is a valid kernel. And because we're sure that the absolute value of this inner product, which is bounded by the product of the norms, is less than r, because I've said that x is inside this r size hole, then I know that my Taylor series is never going to blow up, so my inner product is never going to blow up. So even though I'm using infinitely many features, I'm still guaranteed that I'm in a well-behaved space. So is that clear? So why this is true? Yeah. Okay, so now in every textbook on kernel methods, you will have seen the Gaussian kernel, and this is a valid kernel. And I'm not going to tell you why. This is a fun exercise. But what you will need to use is that the product of kernels, the mapping of some, the product of a mapping of some function is a kernel, and the exponential kernel. So I will give a little clue. So you start with this exponential kernel, and you notice that this norm, when you expand out the norm, you get the exponential kernel and the product of the exponential of the norm of x and the norm of x dash. And from there, you should be able to see, using the rules that we've described, why the Gaussian kernel is a kernel. But now, using all of these rules, we've managed to construct the, I guess, most famous kernel in machine learning, which is used in pretty much all papers. Okay, so questions so far? No? Okay. So a question that I guess is perhaps reasonably tricky is that if somebody gives you a function of 2 arguments, can you tell me if it's a kernel or not? Okay. And this might not be trivial because maybe you can use the rules for constructing kernels from other kernels to find a new kernel, maybe not. Maybe you can find a feature vector that works, but this could be tough, okay? And in any case, the feature maps aren't unique. But there is a property of the function that, if it holds, guarantees you that this is a kernel, and this is positive definiteness. So if the function is positive definite, then it's a kernel. If it's a kernel, then it has to be positive definite, okay? So what is positive definiteness? It's this property here. So here is a kernel. So let's say that you have a collection of n objects and a collection of n scalars, okay? Positive definiteness means that this double sum of scalars ai, aj, kx, ixj has to be non-negative, okay? Strictly positive definite is a stronger condition. It means that it's only 0 when all of the ai's are 0, okay? So this is a core property. But if it's positive definite, then it's a kernel. Kernel, positive definite, okay? So I'm going to prove in one direction. So as long as it's a valid inner product of feature maps, then I can prove that it's positive definite. You can also prove in the reverse direction. I'm not going to do that, okay? But let's go in the forward direction, okay? So let's say that I have a kernel, and I can write it as a product of feature maps, okay? So it's a valid kernel. Now, what is this thing here? It's actually just the norm of the weighted sum of features with this ai. So you can expand this norm out, and you're going to get exactly this expression here, okay? And we know it's a norm squared, and the norm squared is non-negative, okay? It's either greater than 0 or equal to 0, okay? So we've shown that if you have a valid kernel, then it has to be positive definite, okay? You can also prove the other direction, that if it's positive definite, then it has to be a valid kernel. And for that, you can look at the notes, okay? So now, our final, we've got kernel, we've got Hilbert space, now we need to do reproducing. So this is basically getting back to the second intuition about what an RKHS is doing, okay? So, if you're doing Gaussian processes or sort of similar topics using kernels, you're often going to run into something that looks like a function which is a smooth function of its argument. So let's say that, for instance, my kernel is the Gaussian kernel that we now know is a kernel. And we've got some scalars here which can be positive or negative. These are just numbers. And we take some of these kernels. Okay, so now we get this smooth function here. And so, you know, when you encounter reproducing kernel Hilbert spaces, like you're often going to run into functions like that. And you're going to sort of say, well, because it's in the RKHS, it's smooth, it's well behaved, and so on. But what this intuition, I guess, is a bit disconnected from is this idea of kernels as inner products between features, which is what we've talked about so far. So I've sort of really belabored the fact that kernels can be written as dot products between features. But then you sort of say, well, this is a function in this feature space, but it's like a smooth sum of Gaussians. So what does this have to do with the features that we've painstakingly constructed so far? So the main sort of point of the next few slides is to actually show that these are the same thing, and then to sort of link this smoothness idea with this feature idea in the case of kernels. Okay, and the representative theorem is a sort of byproduct of this reasoning. Okay, so I'm going to start again with the very first example I began the lecture with, which is this XOR example, okay, where you have these, you know, red blobs, blue blobs, you want to separate them, and you do that by mapping your two-dimensional vectors into some three-dimensional space of features, which allows you to separate them, okay? So now we know what a kernel is. A kernel is just the inner product between these two features, okay? So this is my kernel between x and y, okay? Now, let's say that I want to define a function on the space x, okay? And I want to define that function in terms of these features that I care about, okay? So these are the features I care about. I want a linear function of these features, okay? So what does this mean? It means that I take a linear combination of each of the features that I have defined, okay? So this can be written as basically some vector, ABC, transpose, times feature vector, x1 squared, x2 squared, x1, x2, okay? So I'm going to now give an equivalent notation for this function, which is going to have a dot in it. So when I have a dot in it, what I mean is the coefficients which multiply the features to define the function. So the reason I put a dot here is because, like, I haven't yet filled in the x, so to speak. So the moment I fill in the x, then I put these guys in here, okay? So dot just means like the function in the abstract. When I put in an x, it means that I've taken the inner product of these three scalars with the three features of the x. Yep? Okay. So now f of x is the inner product of this vector here, f dot, and the feature map at x, okay? So what's interesting about this notation is that the feature map is itself a function, right? So I'm going to write k dot y to denote the function, which is the feature map evaluated at y. So this is like where things get a little bit tricky. So please, again, like ask me if things are not clear, okay? So my feature map at y is a vector with three numbers in it. It's these numbers here, first coordinate squared, second coordinate squared, product of the two coordinates, okay? But I've already told you in the last slide that a vector with three numbers is a function, because I can use that. I can take the inner product with some other vector, and then I can get a function evaluated at x, okay? So I'm going to write this as a function now. I have to put a y here, because this y tells me what's going to go into these entries here. And I'm going to put a dot here because I haven't yet evaluated it at x, okay? And here I can evaluate it at x. I just get, you know, ax1 squared, bx2 squared, where a, b, and c are just given by these entries here, okay? So I haven't done anything like problematic here. But what's sort of weird about this notation here is that, in fact, I could just flip this whole thing around, right? And I could put x dot here and phi of y. And that would be just as valid, because now I would have, you know, these are my features of y, and u, v, w are now my features of x. So this notation and this notation are completely equivalent, because you get exactly the same thing out of it. In fact, you get just the kernel between x and y, okay? So basically, I can equivalently write the feature map of x as a function index by x, where I haven't yet evaluated the second argument, and feature map of y as a function indexed by y, where I haven't yet evaluated the second argument. Okay, and then with these feature maps, I can then take the inner product with some other vector, and then I can get like a function evaluated at x and y. So is all of this clear? Yeah. Okay. So now we've basically seen, just with this simple finite dimensional example, the most important property of a reproducing kernel Hilbert space, which is the reproducing property. So basically, if I have a function and I evaluate it at this feature map of x, okay, so inner product of this ABC set of scalars with this vector of features of x, then I get f evaluated at x, okay? And in particular, if I take the inner product between features of x and features of y, I just get the kernel with x and y, okay? So these are the two properties that you will have seen in textbooks on kernel methods. And like this is the reproducing property. But in fact, like it's not a very difficult thing. It's just a product of the fact that you're taking well, the inner products of features. So it's a very simple idea. Okay. So one interesting point to bear in mind, though, is that the feature maps of the x points are smaller than the larger space of functions that you're considering. So basically, if you have some x, you map it through the feature mapping, you get something which is this kx dot. There might be functions in the space that can never be written as this example. So in the case where your feature vector is this, can someone tell me of a function that can't be written in this form, in this three-dimensional space? So which can't be written as the mapping x1 squared, x2 squared, x1, x2. So remember, the functions have to take the form ABC, where these are just numbers.
So 0, 1, 1?
0, 1, 1, that would probably work. Yes, that would work. Yeah. So you can see that you can't plug in those numbers and get things that are consistent across these, right? Because, yeah, 0 times 1 is 0 here. Yeah. And another example is, what if this number is negative? So there are many examples, in fact. Like this is actually, you've only sort of got 2 degrees of freedom here, but you're in a three-dimensional space. So there's a whole chunk of this three-dimensional space you can't span with these 2 numbers. Yeah. Okay, and this is going to be generally true. So like in a feature space, the space of functions is always, like almost always going to be much, much bigger than the space of mappings of your x's. So this is just a nice point to bear in mind. I put that here because somebody asked me the first time I gave the course about that. So yeah. I even gave away the answer. Okay. So pay attention to this. Okay. So I've shown how the representative theorem works when I just have a finite vector. But again, like in most of the interesting cases you care about in machine learning, the feature space is going to be infinite. So let's see what happens when the feature space is infinite. Okay. So in one example I'm going to show you, you can expand the kernel as an infinite sum of weighted features. Okay. In the next slide I'm going to show you what these look like. But these are just like nonlinear functions of x here. This is a nonlinear function of x, another nonlinear function, or the same nonlinear function. But of a different x, okay? And these nonlinear functions just have a nice property that they're orthogonal to each other. So if you take the inner product of the feature of the ith feature with the jth feature, it's going to be 1 if I and j are the same. It's going to be 0 otherwise. So there's sort of like each feature is capturing a different facet of the problem. Like that's what this is intended to show. In this case, we're going to use the very first infinite example that I brought up, which is that the features have to be square summable. Remember, like even though there's infinitely many of them, as long as the sum of the squared features is finite, then the kernel between these features is well defined. It's not going to blow up. Yep. Okay. And then I'm going to define my function of x to be just these AIs, so these scalars. So remember, the sum of the AIs has to be also squared summable, like it's not allowed to blow up either, multiplied by these coefficients, multiplied by these nonlinear features, okay? So what's an interesting kernel that can be written in this kind of form? It turns out, I don't know, did I write it here yet? All right, yeah. The Gaussian kernel is basically a kernel that has exactly this form, okay? So the Gaussian kernel can be written as this weighted sum of features here, okay? Where these guys here are basically Hermite polynomials scaled by exponentials. So I hope people can see this drawing here, because I've shown here's the Gaussian in dashed lines. Then this thing here, which looks like a less large Gaussian, is the first feature. Okay, so the first feature of x is just a Gaussian. The second feature goes up, then down, then up again. Okay, so it's a bit more wiggly. And you can sort of see that if you take the dot product of the first and second features, you're going to get a 0, because this feature sort of averages out that one. Okay, the third feature, so E3, goes up and down and up and down. Okay, so you can see that as k is getting higher and higher, these features are getting more and more wiggly. Okay, but also the scaling factors for these features is getting smaller and smaller and smaller, okay? So you're basically saying, like, I'm taking into account all of these very, very nonlinear features of my x, but if the features get too wiggly, I'm not going to give them a lot of weight, because probably they're not going to have as much meaning as like a very slowly moving feature of my variable, so like a smooth feature of the variable, okay? And what does this mean? It means that if I've defined my function like this function is going to be smooth. Why is it going to be smooth? Because as soon as this thing gets wiggly, these are going to be very small. Okay, so I'm basically like putting big weights on the ones that aren't too wiggly and small weights on the ones that are. Also remember that the sum of squared AIs has to converge, right? And so because the sum of squared AIs has to be finite, these aren't allowed to blow up. So they're going to have to decay as well. So basically this is getting smaller and this is getting smaller as this index gets bigger. So a function that I write like this is going to be a smooth function, okay? So this is a way of sort of saying, like, how does a feature view result in a smoothness argument for an RKHS? And I'm saying that if you're using infinitely many features, then you're going to ensure that the features that are at high frequencies have small weight, okay? So that a function in this feature representation is going to be a smooth function. Okay, so yeah, I will talk about this slide. So basically, like, the inner product of these two functions we've already done, because it's just the sum of these guys. I can also show that this evaluation of f of x is never going to blow up. Why is that? Well, you just use the same trick that we used to show that this never blew up. Okay, you bound this by the sum, by the product of the norms of the A and the norm of this. This thing here is just the kernel evaluated with itself. This is just the sum of the squared A's, which we've said have to be finite. So that means that f at x is always finite. Okay. So now, let's see how we have the time. Oh, we have time. Okay. So this example is perhaps a little trickier. So who is familiar here with Fourier series, or who has encountered Fourier series? Good. A lot of people. Okay, so I'm going to now write my function as a Fourier expansion. Okay, so here is f at x. Okay, so I can write this as an infinite sum of the Fourier coefficients of f multiplied by these complex exponentials, which is basically cosine Lx plus square root of -1 times sine of L of x, okay? So just as we had before, my representation of the function is a linear combination of nonlinear functions that become more and more, I guess, high frequency as this index increases, okay? Because your cosine at some frequency where the frequency is sort of going up and up and up as your L grows, okay? So this is the Fourier transform of some function. It's on a periodic domain, so this is why this is a sum and not an integral. Okay. So let's say now that my kernel function is just the kernel of a difference between x and y. So it's a kernel of a single argument. So this means that I can also take the Fourier transform of the kernel function. Okay. So let's just say that I have some argument here. I can write kernel of this argument as the sum of the Fourier coefficients of this kernel times this exponential here. Okay, so I'm also representing my kernel in terms of a weighted sum of these increasingly high frequency functions. Okay. So because the kernel is positive definite, I won't prove it, but k and its Fourier transform in this case is real and symmetric. Okay. So this is my kernel, this is my function. So now I'm going to define a feature vector as I did before for this function in terms of its Fourier transform, and show that all of the stuff that we need to work is going to work. So all of the things we needed for the kernel trick function. Okay. So my function here, I'm going to define with this dot notation as the Fourier coefficients divided by the square root of the kernel Fourier coefficients. Okay. So if that's the case, then my inner product between two functions is just the inner product of these coefficients divided by the product of the square root of the kernel coefficients. Okay. And I'm going to define my feature map as just the square root of the Fourier coefficients times these complex exponentials. Okay. So if I've defined f like this and my feature map like this, then let's check that everything works. Okay, so first of all, we want that the inner product of f and k is equal to f at x. Okay, that's the first trick for the reproducing theorem. So let's see. So we've got f, which is the Fourier transform of f divided by the square root of the Fourier transform of k. Here we have this thing here denotes the complex conjugate because we're taking an inner product in a complex space. And here is the representation of the features for x, which is square root of k times that. This just cancels out, and you just get the Fourier transform of f. And that's f at x. So this is working. Okay. The second thing we wanted to check is that is this inner product between two features equal to the kernel between x and y. Okay. So that is true. So here are the features of the kernel of x, square root of k times that, square root of k times this. If you take this product, you get basically the Fourier transform of x of the argument here, which is just the kernel at x minus y. Okay. So is all of this, is this reasoning here clear? So if I started with this as my function and this as my feature, then I've shown that the reproducing property holds both for the function here, because these k's cancel. So this one comes from f, and this one comes from the feature map of x. And because the feature map of x has the square root of the Fourier transform of k here, I take the product of these two, I get this. And then as a result, I'm just getting back the Fourier transform of k of x minus y. So this property also holds. Okay, so the two properties that I care about are holding here. Okay. So I've shown that this works. So I think another interesting question is why on earth would you do that? That's hopefully on this slide. So what is the point of defining a feature map of f, which is the Fourier coefficients of f divided by the square root of the Fourier coefficients of k? Like, why is this a good or useful feature map? So one answer is that the norm of f can be then written as the product of the Fourier coefficients of f divided by k. So this is actually a pretty sensible thing. So for instance, if I had a Gaussian kernel, so if my kernel was just a Gaussian, then what would I know about these Fourier coefficients of my kernel? So what are the Fourier coefficients for a Gaussian? So these are also decaying as a Gaussian. So the Fourier transform of a Gaussian is a Gaussian. Okay. So if I know that if I start with a Gaussian kernel, then these k's are going to decay very, very quickly. Okay, they're going to decay like a Gaussian. So if these are going down very fast, then 1 divided by this is going up very fast. Okay. So that means that if I want this sum to be less than infinity, then this product here has to be decaying faster than these are going up. Okay? So if I use any kernel, like a Gaussian kernel, these will decay exponentially fast, very fast. If I use a Laplace kernel, so that's e to the 1 norm of x minus y, these will decay polynomially. Okay? So this will increase polynomially. So basically, this sum here, for this sum to be finite, so for f to be in the RKHS, for it to have a finite norm, the Fourier coefficients of f have to decay faster than the inverse of the Fourier coefficients of the kernel. And any kernel is going to have fast decaying Fourier coefficients, so that means that these will have to decay fast. Now let's go back to the definition of f. F is this Fourier coefficients times these sinusoids of increasing frequency, right? So basically I'm going to say that these have to decay very quickly, and hence as soon as these become non-smooth, they will have a very small weight if we're going to require this to hold. So is it clear now why this is a sensible feature map? Like why we want to penalize f by 1 on the square root of the Fourier coefficients? Okay. So this is like a very sort of nice way to look at why RKHS functions are so. Okay. So I've shown now, well, 1 finite feature space example and 2 infinite feature space examples. Of the reproducing property and I guess generally of the feature space construction. So the core results for an RKHS are the following 2 results. So first of all, we want the reproducing property to hold. And second, we want that the kernel, with one of its arguments fixed, is itself a function in the RKHS. Okay. Which means that, of course, the inner product between 2 such kernels is just the kernel with one of its arguments at x and one at y. So this is actually pretty neat because, I can define an infinite feature space and I can describe an algorithm on it. But I never need to care about this infinite feature space as long as I know the closed form expression for the inner product between these infinite features, and as long as I can express my learning algorithm only in terms of this inner product, then I can I can use these infinite features and define my learning method with them without ever having to care about writing them out explicitly, which generally you can't. So this is quite I think neat property. Like you have this power of this infinite feature space, but you never have to write the features down. So this is one definition. There's actually another definition that I'm also going to introduce, which is a little bit more technical, but also very important. So reproducing kernel Hilbert space is a space with a reproducing kernel. That is pretty obvious. Here's a second definition of a reproducing kernel Hilbert space, which is basically that we want the operator of evaluation to be bounded. So this is a functional analytic definition. What does it actually mean? It means that the thing that takes your function f and evaluates it at x has a certain property, the boundedness property. What does that mean? It means that evaluating it f at x is always upper bounded by some number, which is a function of x, times the norm of f. Okay? So this is boundedness. Now this might just sound like a mathematical game, but it's actually one of the most useful properties that a function space can have. And the reason is because boundedness implies that if 2 functions agree, like if in the norm on the space of functions, I think that they're the same function, then they agree at every single point. Okay, so let's go through the proof. So I'm saying that f at x minus g at x, okay, is the evaluation of f minus g. So this thing here just takes f and replaces it with f at x, and takes g and replaces it with g at x. Okay. Now, this boundedness tells me that this is upper bounded by this number here times the norm of the difference of f and g. Okay. So I'm just applying this property down here. Okay. Now this is interesting because if my optimization algorithm has said that, you know, the difference between, say, my current solution and the best possible solution is 0 in norm, that means that they agree, they make the same prediction at every point. So if I'm trying to use my function to make a prediction, I want to make sure that if my solution sort of works in the kernel space and says that I've reached the best answer according to some kernel norm, that I'm making the same prediction as the best function would be making. Okay, so this is a sort of property saying that if I'm using these functions in learning, then I can say something about their prediction at every point. So this is a property that a lot of richer function classes don't necessarily satisfy. And this is a big reason why, at least in learning theory, a lot of people like working with reproducing kernel holistics. Okay, so is that property clear to everybody? Yeah. Okay, so this seems to have absolutely nothing to do with what I talked about before. Actually, it's extremely related. Basically, if H has a reproducing kernel, if the reproducing kernel property holds, then this is true. And vice versa. If this is true, then it has to have a reproducing kernel. So that's very exciting. So I'm going to prove just one direction, which is that if, I'd hope for better music, it's a good theorem. Anyway, if this has a reproducing kernel, then this is bounded. You can prove the other direction. I'll do that in the advanced part of the course. But this direction is actually really easy, okay? So this is the evaluation operator at x, so f at x. We know, because of the reproducing property, that f, this is equal to the inner product of f and k of dot x, okay? Now, we can upper bound this by Cauchy-Schwarz as the product of the norm of this function here and the norm of this function here. Okay. Now we know that the norm of the k dot x is just the inner product of k dot x in itself, which is by the reproducing theorem k of x and x. So that is hopefully clear. And so basically, what I've shown here is exactly the boundedness property. I've said that dx of f, so the evaluation of f at x, is upper bounded by the norm of f and some lambda, which depends on x, which is exactly this thing here. Okay, so I've shown that if the function space has a reproducing kernel, then the operator of evaluation is bounded. Okay, and it's also possible to show the other direction. So I can start with the bounded evaluation operator, and I can use that to construct a reproducing kernel. So the proof is actually not hard at all, because I'm basically just grabbing a proof that someone already did and using it. But yeah, that part I will talk about later. Okay, good. So the very last theorem I'm going to talk about, I think today, is the Moore-Arancian theorem, which is that every positive definite kernel has a unique RKHS. Okay? So if somebody gives me a kernel, and if I can show it's positive definite, then I know that there is an RKHS for which that positive definite function is a reproducing kernel. And conversely, if I have a reproducing kernel Hilbert space, then I am sure that there is one and only one kernel which satisfies the reproducing property for that space. So the kernel uniquely defines the space. This is important because I've already shown you that the feature map is not unique at all. In fact, for any interesting case, there's going to be infinitely many feature maps that give you the same kernel. So a feature map doesn't define the space, but the kernel defines the space uniquely. And the proof of this is perhaps 1.5 hours long, so in this lecture. Okay, and so yeah, I mean the function that I introduced earlier, just as a reminder, it's this linear combination of Gaussians. I've already shown you what the feature map looks like for the Gaussian kernel. So I could write this linear combination of Gaussians as an inner product of some scalars and these Hermite polynomial sort of wiggly features that I introduced earlier. Okay. So this is our sort of short summary. Reproducing kernels, positive definite functions, they're always the same. And these are also these also uniquely define Hilbert spaces with continuous evaluation operators. Okay. I think actually I have 10 minutes, so I'm going to just quickly give a very cute and simple example of a kernel algorithm, which is basically, let's say that I've got m points x and m points y. Cool. I have a t-talk. Yeah, and I want to know what are the difference in means of these in feature space. Okay, so I'm going to just do it on the board. Okay, so let's say that I've got xi, I in 1m, and so on, and yi as well. And I'm going to just say that they're the same number of points for each of them. Okay? So what is the difference between their means in feature space? I'm going to say that I'm going to show that you can find the distance between the means without ever having to evaluate these sort of infinitely large features. Okay? So the trick is that you've got sum over I, 1 on m, phi of xi, that's the mean of the I point in feature space, minus 1 on m, sum over I, phi of yi. Okay? And let's just say I'm going to take the squared norm of the distance between these means. So let's just look at the, so this is going to just be the inner product, 1 on m, I, phi xi minus phi yi. And I'm using the fact that there's the same number of points for xi and yi. And the same thing, 1 on m, sum over I, same thing. Okay, so now let's just look at the inner products between the phi xi terms and themselves. Okay, so I'm going to have the phi xi, phi yi, and phi yi. So I'm just going to look at the first term. So I've got 1 on m squared, sum I equals 1 to m, j equals 1 to m, inner product of phi xi, phi xj, plus all of the cross terms, plus all of the y terms, okay? But what we know is that the inner product of the feature map at xi and the feature map at xj is just the kernel between xi and xj, right? So that's 1 on m squared, sum over I, sum over j, k, xi, xj, plus, and then you're going to have I, j, m squared, k, yi, yj, and the kxi, yj terms. So what I've done here is I've shown that the norm of the difference in feature means can be expressed entirely in terms of kernel functions between the xi's and xj's, kernels between xi, yj, and so on. So is that reasoning clear to everyone? Are there questions about this? Yeah? Okay. So this is kind of cute. So a good question is like, why would you care about the difference in means? Okay, this is sort of the simplest kernel algorithm you can do. It's just like I compute the means of my x's, I compute the means of my y. Is these means different or are they the same? So there is, even for something as simple as this, there's already some very powerful things you can conclude. So let's say first of all that your feature map is just x by itself. Feature map of x is just x, okay? So then this is just the norm of the difference in means. So if x and y have different mean, and this norm is 0, then you're saying, well, the means are the same. But now what happens when we start using clever features? Well, here is a feature of x, which is just x and x squared. If I'm using this very slightly clever feature, what I can already distinguish is both the means and the variances. Okay, so now I'm saying, well, if the mean is the same and the variance are the same, then this is going to be 0. So what I've talked about just a moment ago is kernel spaces where there's infinitely many features, so the Gaussian kernel, for instance. So what I'm going to be showing in later lectures is that for these infinite feature spaces, the norm of the difference in means, like in the infinite sample limit, is 0 only when p and q are the same in every detail. So means have to be the same, kurtosis, variance, like every statistic is the same. So even something as simple as a difference in means, if you have a large enough feature space, can tell you everything there is to know about the distributions that generated these x's and y's. So that's just like a little preview of stuff. Okay, so I will stop here, I think, and yeah, hopefully, well, see you on Thursday or Dave.
Yeah.